Published more than 150 papers, and is a well-cited scientist. He has served in many national committees, including NSF and the US EPA and National Academy of Science in US. He received many awards, including Pettenkofer Award, which is the highest award of the International Academy of Indoor Air Science. Let's welcome Professor Charles Weschler.
Friday afternoon, I'm impressed that so many of you have come to this lecture on indoor chemistry, chemistry that occurs indoors. Indoor environments can be viewed as reaction vessels. We have chemicals that enter from outdoors. We have chemicals that are emitted indoors. And some of these chemicals, they react with one another. It's important to consider these chemical reactions because they change the nature of the chemicals that are present indoors. They change the concentrations of chemicals indoors. They change the types of chemicals that you might find indoors. I think most of you are probably quite familiar with atmospheric chemistry. And we've learned a great deal about atmospheric chemistry over the last 4 decades. A lot of money has been spent around the world studying atmospheric chemistry. Now, indoor chemistry, in some ways, it's similar to outdoor chemistry, but there's important differences. Different reactions dominate indoors compared to outdoors. And the reason for this is because of these different factors indoors compared to outdoors. We have less direct sunlight, which means photochemistry is less important indoors than outdoors. The temperature fluctuations are smaller indoors compared to outdoors. It doesn't rain indoors. This means that we don't have this cleansing action of rain on the indoor atmosphere. The surface to volume ratios indoors are much larger than the surface to volume ratios outdoors. This means surface chemistry is more important in indoor environments than outdoor environments. And finally, indoors we tend to have much higher levels of organic compounds than we do outdoors. And this is true even if we're talking about tropical rainforests. On this slide, I've summarized some of the species that are most abundant in tropical rainforests. Isoprene, various terpenes, acetone, methanol, ethanol. The green bars, those are the concentrations of these chemicals along the x-axis in the canopy of a tropical rainforest. The rainforests that I looked at were from the Amazon, from Borneo, and from Costa Rica. These rainbow-colored bars, those are typical indoor concentrations based on surveys of many different indoor environments. The only compound on the x-axis which exists at comparable concentrations in the tropical forest and in a room such as this is isoprene. Why do we have isoprene in this room? Because we exhale it. It's on our breath. The isoprene levels in this room right now, given the number of people I see, and what I'm guessing is the air exchange rate, the isoprene levels are probably between 2 and 4 ppb in this classroom. In a tropical forest, you see similar levels. But then for alpha-pinene, for limonene, for acetone, for methanol, for ethanol, the concentrations in this room, the concentrations in a typical indoor environment are on the order of magnitude higher than in a tropical forest. And certainly much higher in typical outdoor environments. This has implications for things like free radicals. We have a lot of organics to react with free radicals indoors. This will reduce the lifetimes of some of the free radicals. Indoor environments are very diverse. We have different types of rooms in a home. We have living rooms, we have kitchen, we have bedrooms. The homes themselves are quite diverse. We have apartments, we have row houses, we have detached homes. And of course, where these homes are situated That's diverse. But there are commonalities among indoor environments. In a given geographical region, the sources of chemicals tend to be fairly similar. People buy their products at the same stores. I've already mentioned surface to volume ratio, and the fact that surface to volume ratios are so much larger indoors than outdoors. These large surface to volume ratios, that's another commonality, meaning that in most indoor environments, the surface chemistry is very important. Most rooms have lighting. Perhaps it's windows, perhaps it's artificial lighting, maybe it's a combination of both. Most of the indoor environments we're interested in are occupied. And us, the occupants, we lend a certain commonality. We leave our skin oils behind. We leave our skin flakes behind. Desquamation. Desquamation is a fancy word that simply refers to shedding skin flakes. We replace our skin every 2 to 4 weeks, and we shed our skin flakes at a really high rate. We shed these skin flakes, 200 to 6,000 flakes a minute. And that's happening right now in this room. So if you look to the person to your right or left or in front of you, you're sharing their skin flakes. And there's some really interesting studies on this, including recent studies on microbes and viruses identified from gene sequence analysis and skin flakes. So these skin flakes are being shed at about 30 to 90 milligrams per hour. Occupied environment, you find the skin flakes on all the horizontal surfaces, and you find skin oils on surfaces. So this is another aspect of commonality in occupied indoor environments. Surface films. Indoor surfaces might begin as quite different from one another chemically. That glass surface, when it's new, is very different from the surface of this podium when this podium is new. But over time, the glass soils and this surface soils and this floor soils and the very thin films at the surface, they're similar over time. They contain these skin oils. They contain particles that have deposited from the air. The vertical surfaces, it's primarily the fine particles, but the horizontal surfaces, they soil with both fine and coarse particles. The chemicals that are found indoors, some of them are exclusively from outdoors. Some of them are exclusively from indoors. Some are a mix. And some are a consequence of chemistry. And that chemistry might involve an outdoor species such as ozone reacting with a species emitted indoors from a cleaning product, limonene from a cleaning product. It might be the result of 2 indoor species reacting, or for that matter, 2 species that originated outdoors, came in indoors, and then reacted. It's interesting to recognize that the chemicals in our indoor environments in 2015 are quite different from the chemicals that your parents or grandparents grew up with. We use different products. Plasticizers and flame retardants. They're common today in indoor environments. But those plasticizers and flame retardants, many of them didn't even exist 50 years ago. The plastics we use indoors, the polymers we use indoors, many of them did not exist 50 or 60 years ago. You look around this room right now, and we have so many different polymers, so many different things that contain plasticizers or flame retardants. And it's even more if you go into something like a typical living room. The buildings are built differently today. We use different materials. We use pressed wood products today rather than lumber. The buildings are tighter. We're trying to save energy. The buildings are much tighter than they were 30, 40, 50 years ago. And that's true not just in the United States or Europe, but that also is becoming true in China as well. The newer buildings are constructed tighter. Our building operation, a big difference in the way we operate our buildings is air conditioning. The This classroom is air conditioned. In terms of air exchange rates, because this classroom is air conditioned, the air exchange rate is relatively low. I would guess it's around half an air change an hour, maybe less. If this were not an air-conditioned classroom, we'd have our windows open right now. Perhaps we'd have fans on. The air exchange rate would probably be between 5 and 10 air changes an hour. This has a huge difference in terms of the concentrations that chemicals which originate indoors can achieve in indoor air. At 5 air changes an hour, toluene being emitted from this podium is going to have a much lower steady state concentration in this room than it would, much lower than it would at half an air change an hour. Steady state concentrations would be much higher. Personal habits are changing. In the United States and Europe, indoor smoking is much less common than it was just 20 years ago. I think we're seeing that change happen in China now as well. Certainly when you go to restaurants, you don't see as much smoking as you did just 3 or 4 years ago. And I think we're seeing less smoking in public spaces, and I think that will continue to change. And of course, smoking introduces all sorts of chemicals indoors. When we talk about indoor chemistry, the chemistry can occur in the gas phase, it can occur on surfaces. Temperature influences both types of reactions. Air exchange rates has a larger influence on gas phase chemistry. I'll say more about this in a moment. Temperature and relative humidity, they have a larger influence on processes which occur on surfaces. So a little bit more about this connection between chemical reactions that occur indoors and ventilation rates. Whether we're talking about gas phase chemistry or surface chemistry, heterogeneous chemistry, ventilation removes pollutants that originates indoors, and ventilation brings outdoor pollutants indoors. For gas phase reactions, ventilation limits the time available for the molecules to react with one another. If the ventilation rate is high, you're sweeping the chemicals out of the room before they have a chance to react, unless the reaction rate between the chemicals is really fast. In terms of surface reactions, ventilation affects the boundary layer. The higher the ventilation rate, the higher the near-surface airflow, the thinner the boundary layer, and to the surfaces themselves. This slide lists some of the more important reactions that occur indoors. Oxidation reactions, hydrolysis reactions, acid-base chemistry, decomposition reactions, photolysis, dehalogenation. Now the class of reactions that's been studied the most is oxidation reactions. And we'll say a fair amount about oxidation reactions. But I'm going to begin with a slide on hydrolysis indoors and another on photolysis indoors. And these are areas that are only now beginning to receive attention. We'll begin with the case of 2-ethylhexanol. A large amount of 2-ethylhexanol is produced by the various chemical industries around the world. But most of this 2-ethylhexanol is simply a step on the way to different esters. If you think of a very common phthalate ester, di-2-ethylhexylphthalate, DEHP, this is an example of an ester that's being produced in enormous quantities, and one of the starting materials is 2-ethylhexanol. Very little 2-ethylhexanol winds up by itself in a product, in a commercial product. Yet, in this large study conducted by the US EPA of different chemicals found in indoor air, they found 2-ethylhexanol 100% of the time in the different buildings they looked at. Where was the 2-ethylhexanol coming from? I think most of it was probably the result of hydrolysis of esters such as di-2-ethylhexylphthalate, DEHP, or the di-2-ethylhexyl adipate or sebacate. These compounds are so common indoors, especially DEHP. There are a number of reports in the literature of 2-ethylhexanol being emitted from vinyl flooring that's been laid down on moist concrete. Think about hydrolysis. It's often base catalyzed, right? So if you have improperly cured concrete, if you have moist concrete, you have a highly basic surface. The pH is probably up around 11 or 12. Put the vinyl flooring down on it, the PVC, and the vinyl flooring might be 30% by weight, even 40% by weight, plasticizer, DEHP. So the conditions are right to hydrolyze the DEHP and produce the 2-ethylhexanol. There's a couple of other reports in the literature on hydrolysis of other chemicals. TXIB, that's this molecule. TXIB is a relatively inexpensive plasticizer. If you think of grips on hand tools, those kind of soft plastic grips, often they're plasticized with TXIB. Well, there's a report in the literature on TXIB hydrolyzing Texanol isomers. This is Texanol. You almost always find Texanol in a room if it's been painted with latex paint. Texanol is a coalescing agent in latex paint. So this is something other than the hydrolysis of TXIB. The major reason we find Texanol indoors is because of its use in latex paint. There are two other reports in the literature on Texanol hydrolyzing over time into various hydrolysis products. I also think it's likely that in some indoor environments, microbes contribute to the hydrolysis product. We know certain microbes contain enzymes that promote hydrolysis. So I would not be surprised if we find in future studies that microbes in indoor settings are contributing to the hydrolysis of some of these common esters. Now the topic of photolysis. Photolysis has received very little attention indoors until the past year and a half. Just this year, a paper came out in Atmospheric Environment that described the photolysis of nitrogen dioxide indoors, NO2, to produce nitrous acid, HONO. The levels that were produced in this particular study were not that high, about 1.5 ppb being produced by photolysis. Now, for many years, it's been recognized that NO2 indoors is a source of HONO, nitrous acid. Indeed, nitrous acid indoors reaches concentrations much higher than nitrous acid outdoors because it doesn't photolyze the nitrous acid itself as fast indoors as outdoors. Levels indoors as high as 20 ppb have been measured for HONO. But it does appear now that the photolysis of NO2 is also contributing to indoor HONO, in addition to the disproportionation of NO2 on indoor surfaces to give HONO and nitric acid. Now, what I find much more exciting than the photolysis of NO2 to create HONO is the photolysis of HONO to make hydroxyl radicals. A paper reporting this appeared in PNAS a little more than a year ago. In this study, the researchers used laser-induced fluorescence to measure the hydroxyl radical indoors in real time. They measured, at some times during the day, they measured hydroxyl radicals in this classroom. It was a classroom they were studying, something like this classroom. They measured indoor OH comparable to what we measure outdoors in the afternoon. As a matter of fact, their highest levels were when the sun was shining through a window, as is happening here, and they could actually measure in this area where the sun was coming in and where there was HONO, simply because it was present indoors, they could measure significant amounts of the hydroxyl radical. So this is causing us to rethink hydroxyl radical chemistry indoors. We've previously thought that most of the OH indoors is a consequence of ozone reacting with alkenes, especially terpenes. Now we have to pay more attention to photolysis. So having said that little bit about hydrolysis reactions and photolysis reactions, let's talk about, let's talk about oxidation chemistry indoors. But there's one more slide on indoor photolysis. I think it's interesting that indoor photolysis is probably changing as I speak. Our windows are changing. We're going from single pane windows to double and triple pane windows. We're using more tinted windows. I think there's a chance that this window might be tinted. It certainly looks like it's double glazed, right? So that will affect the spectrum and the intensity of the light getting through the window into this room. And then, of course, in terms of lighting, the old types of lights, incandescent lights, fluorescent lights, they're being replaced with CFLs, compact fluorescent lights, and LEDs. So this is still another reason why the intensity and spectral distribution of indoor light is changing. And this, of course, will affect the photolysis that I was just talking about. So now, let's go on to oxidation reactions indoors. Ozone tends to be the driver of indoor oxidation processes. Ozone reacts to produce other oxidants, Kriege intermediates when it reacts with alkenes. I mentioned a moment ago hydroxyl radicals when the reaction with alkenes. Hydroperoxyl radicals, methyl peroxyl radicals, hydrogen peroxides, organic peroxides. Ozone can react with NO2 indoors to make nitrate radicals. Oxygen is also an indoor oxidant, but it's too slow for most reactants. It tends to be nowhere near as significant as ozone in terms of oxidation processes indoors. I think this area of Kriege intermediates indoors is fascinating, and it's received almost no study at all. There are no measurements of Kriege biradicals indoors. Now, a paper came out in Science just a couple of months ago, which talked about formaldehyde oxide. That's the Kriege intermediate form when ozone reacts with ethylene. And this paper presented evidence that the dominant reaction of formaldehyde oxide is with water dimers in the atmosphere. Very nice study. Is this going to be true indoors for formaldehyde oxide? Not necessarily. Organic acids can compete with water and water dimers, and perhaps indoors with much higher levels of organic acids, perhaps indoors the organic acids are competing with the water dimer or the formaldehyde oxide. But I think an even more interesting area are the Kriege intermediates formed from ozone reacting with terpenes, compounds such as limonene or alpha-pinene. Terpenes are very common indoors. They're common because they're used as a scenting agents in so many products. When ozone reacts with a terpene, you get Kriege intermediates that are much larger than formaldehyde oxide. And these larger Kriege intermediates, we anticipate that they'll react with water at a slower rate. So what's the fate of these Kriege intermediates formed from ozone terpene reactions? I think this is a quite interesting question, and we'll see what the answers are, hopefully in a few years. The ozone in this room, most of the ozone in this room has come from outdoors. There are indoor sources of ozone: photocopiers, laser printers, ozone generators. Anytime you have an arc, anytime you have a spark, you make ozone. Xing is looking at the possibility that some combustion processes may be a source of ozone. That's an area of active research right now. Indoor levels of ozone are normally lower than outdoors, and there's large variations with time of day, season, even day of week. Ozone outdoors, it's a consequence of the sun, H-nu, working on this mix of organic compounds, VOCs, and nitrogen oxides. Without the sun, you don't make ozone. So your levels of ozone go up during the day, peaking in the afternoon, they go down at night. In an air-conditioned room, ozone tends to be a small fraction of the outdoor ozone because of the low air exchange rates. At moderate air exchange rates, indoor levels might be 10 to 30% of outdoors. At high air exchange rates, indoor levels can be 50 to 70% of outdoors. At the bottom portion of this slide, I've simply shown indoor-outdoor ozone ratios is a function of air exchange rate, assuming that the first order rate constant for surface removal is something like 3 reciprocal hours, which is a typical value for ozone removal by surfaces in a room. Ozone only reacts at a moderately fast rate with compounds that have a carbon-carbon double bond. The pollutants in this room, the organic pollutants in this room, only about 10% of them have carbon-carbon double bonds. In other words, only about 10% of the pollutants in this room will react with ozone fast enough to compete with air exchange. Compounds such as N-hexane, cyclohexane, hexanol, benzene, formaldehyde, toluene, they don't react with ozone. They don't react with ozone at a fast rate. So you can't use ozone to clean pollutants out of indoor environments, despite what some things on the internet say. And for that matter, when ozone reacts with something like limonene or oleic acid or squalene, it doesn't take it all the way to CO2 and water. No, instead you get different products, and some of these products are less desirable than limonene itself. So again, using ozone to clean the air, not a good idea. Ozone can react with these organics that have double bonds, either in the gas phase or on surfaces. I've talked about some of these free radicals produced. You also get stable products, such as formaldehyde, or dicarbonyls, or dicarboxylic acids. We get peroxides, hydrogen peroxides and organic peroxides. Interestingly, we also get short-lived organics, such as secondary ozonides, peroxyhemiacetyls, alpha hydroxy hydroperoxide. I say interestingly because these compounds live long enough, some of them, to be inhaled. So what happens when you inhale something like a secondary ozonide? We don't really know. It hasn't been studied. For that matter, we don't really know what the concentrations of these short-lived organics are indoors. They haven't been measured. We know from our mechanistic understanding of the chemistry that they must be formed. But no one's measured these compounds indoors. And I think they may have consequences for human health. Ozone chemistry can have a dramatic effect on the mix of chemicals in indoor air. And that's what I try to show on this slide. This is an experiment we did at Lawrence Berkeley Labs back in 1991, quite a few years ago, before most of you were born. On the left, you see the chemicals present in the air of a 20 cubic meter chamber that was being ventilated at 1 air change an hour. And on the floor of this chamber, we had a new carpet. So the major chemicals present in the chamber were styrene, 4-phenylcyclohexene. If you smelt this, you'd say, oh, that smells like a new carpet. It's really remarkable how much 4-PCH smells like what we think to be new carpet. Formaldehyde and acetaldehyde. Those were the major chemicals in the chamber air when there was no ozone in the chamber, just the new carpet. We then introduced a relatively small amount of ozone, so that the concentration of ozone in the chamber was now 28 ppb. Look at the change. The concentration of styrene goes down by about a factor of 2. The concentration of 4-PCH goes down by even more than a factor of 2. Ozone's chewing up these compounds. It's reacting with them. But it's making products. The concentration of formaldehyde goes up by more than a factor of 2. The concentration of acetaldehyde goes up dramatically. And now we see hexanal, heptanal, octanal, and nonanal. So this is a C6, a C7, a C8, a C9 aldehyde that were beneath our detection limits when there was no ozone in the chamber. Ozone reacts with a number of chemicals present in our skin oils. Our skin oil contains squalene. Our skin oil is about 10% by weight squalene. Our skin oil contains unsaturated fatty acids. The sum of these unsaturated fatty acids is roughly equal to the concentration of squalene. So these are two important constituents of our skin oil that react with ozone, and react with ozone very fast. Our skin oil also contains cholesterol, but the reaction of ozone with cholesterol is relatively slow. So this is not an important chemical in terms of reacting with ozone in typical indoor settings. We also have a number of other antioxidants in our skin oil: vitamin E, ubiquinone, lycopene. But the concentration of these chemicals is so much smaller than the concentration of squalene or the unsaturated fatty acids that in terms of reacting with ozone, they're not that important. The really important species are squalene and the unsaturated fatty acids. Let's look at squalene a little more carefully. It's really kind of a cool molecule. 30 carbon atoms, 1, 2, 3, 4, 5, 6 double bonds. How many mammals do you think have squalene in their skin oil? Any guesses? So Professor Jiang says all of them. Well, actually, and I understand why you say why, actually there's only 4 mammals that have squalene in their skin oil. We're one, otters are another. I forget what the other 2 are. Okay? No primate other than man has squalene in their skin oil. Now, we have squalene in all over our body. Many different tissues synthesize squalene. But the squalene is being synthesized on the way to cholesterol. Okay? But in the sebaceous gland, that process doesn't go to cholesterol. That process stops at squalene. And the sebum that comes out of the sebaceous gland, that contains the squalene. So I think that's quite interesting. And obviously squalene is an important antioxidant as far as our skin is concerned. So squalene will react with ozone. Here and here, the reaction makes acetone. If ozone attacks here or here, the primary product is 6-methyl-5-heptene-2-one, 6-MHO. If it attacks here or here, the primary product is geranyl acetone. So these are primary products. Ozone reacting directly with squalene. Ozone can also react with 6-MHO. It's got a double bond. Or it can react with geranyl acetone. It's got a double bond. Actually, it has 2 double bonds. To produce this compound, 4-OPA, 4-oxopentanal, of dicarbonyl. So 4-oxopentanal is what we call a secondary product, whereas these are primary products. Acetone, 6-MHO, geranyl acetone, they're pretty innocuous. We can tolerate quite high concentrations of these compounds. 4-OPA, it turns out that this is an irritating compound. And a number of studies have been carried out at NIOSH, National Institute of Occupational Safety and Health in the United States, looking at the toxicity of 4-OPA over the past 5-6 years. So as I said, it's an irritant. A word about the unsaturated fatty acids. The major unsaturated fatty acid in our skin oil is cis-hexadecianoic acid. It's 5 to 6% of our skin oil by weight. When it reacts with ozone, one of the products is decanal. There's other chemicals, other unsaturated fatty acids that are in our skin oil and produce decanal. So decanal is a marker of ozone skin oil chemistry, as is 6-MHO and geranyl acetone and 4-OPA. And if we were to take a sample of the air in this room right now, you'd see all of them, because of us and because we've got significant ozone outdoors today. I'd like to show you results from an experiment we did at Technical University of Denmark back in 2009. My colleague on this was Armin Visthaler. Armin Visthaler has done a tremendous amount of work both making PTRMSs, proton transfer reaction mass spectrometers, and using them. And in these experiments, we used one of Armin's PTRMS to look at the air in a simulated office. It was actually a 30 cubic meter chamber, sparsely furnished. It didn't look as fancy as this office, and ventilated at 1 air change an hour. We did 2 experiments. In the first scenario, we established a steady state concentration of ozone in the office, and then we had 2 people enter. In the second experiment, we first had the subjects in the office before we introduced the ozone. So let's begin with the first scenario. So we established our ozone level at about 33 ppb. You see from 8 to 10, nothing's changing. The ozone's steady at around 33. At 10 in the morning, 2 people enter this simulated office. Immediately, the ozone starts to fall. Immediately, the 6-MHO, being monitored in real time with the PTRMS, the 6-MHO starts to rise. It takes a little bit longer for the 4-OPA to begin to rise. Remember, this is a secondary product, not a primary product. The ozone, by 1 in the afternoon, is down to about 17 ppb. So it's cut in half just by 2 people entering the office at 1 air change an hour. The 6-MHO reached steady state around 1:30 at about 2.3 ppb. At 2:30, the 4-OPA was still climbing. It hadn't reached steady state yet, but it had reached about 2 ppb. So that's the first scenario. Now remember, in the second scenario, we first have the people enter. That occurred at 10 in the morning. We see a slight increase in 6-MHO when our occupants enter. That's the only change. At noon, we turn on our UV lamps, which are generating ozone. The ozone does not go up immediately. There's a lag. It takes maybe 20 minutes before we see the ozone start to increase. That's the purple line. And at the same time, the 6-MHO start to increase. The ozone has 1, and it's at around 13, 14 ppb. The 6-MHO was still climbing when the occupants left at 1:30. As soon as the occupants left, the ozone started to climb again. The 6-MHO started to go down, but even though the occupants had left, 4-OPA is still rising slightly because it's a secondary product. Altogether, in these experiments, Armin Wisthaler identified 18 different carbonyls, dicarbonyls, and hydroxyl carbonyls in the gas phase. We made no attempt to determine what was on the surface of our 2 volunteers, what was on their skin surface as a consequence of this chemistry. We know what we anticipate to be on the surface. We understand from the Kriege process, the Kriege mechanism, ozone reacting with an alkene. But there have been no measurements today on what's actually on the skin surface as a result of this chemistry. The reaction between ozone and alkenes indoors to produce secondary organic aerosols has been very well studied. There's over 35 papers in the peer-reviewed literature on ozone alkene chemistry as a source of SOA indoors. The reaction that's been studied the most is the reaction of ozone with limonene to generate SOA indoors, reflecting the fact that limonene is so common indoors. More recently, we've looked at the impact of human occupancy on ozone alkene chemistry to generate SOA indoors, and I'll present a few slides on that. And we've also looked at the formation of SOA indoors simply by heating a surface onto which semi-volatile organic compounds have sorbed, have adsorbed or absorbed. So let's first look at experiments conducted at the National University of Singapore. These were conducted in a 240 cubic meter chamber, and the principal investigator was Mashoud Badai. In these experiments, the outdoor air was passing through the chamber, the simulated classroom at 1 air change an hour. The HVAC system recirculated a large fraction of the air. So the air exchange rate with the recirculated air was 7 air changes an hour. The outdoor air mixed with the recirculated air before passing through a bank of filters and being distributed by the supply diffusers. We looked at a scenario where there were no occupants in this classroom and where there were 18 to 20 occupants. In both cases, we were making ozone with UV lamps, and we were emitting limonene from a diffusion tube. So, in the absence of occupants, we were trying to get an ozone concentration at steady state of around 60 ppb and a limonene concentration at steady state of around 30 to 35. And you'll see what happens when we have occupants. So let's first look at the ozone results. So the two traces at the top, the solid blue and the solid purple. These are for experiments that were run with no occupants in the simulated classroom. And overall, these experiments lasted for 5 hours. At 45 minutes, for the occupied conditions, that's when the occupants entered, right here. So unoccupied, the ozone reached a steady state value close to our target, around 60 ppb. Occupied, the level was between 35 and 40 ppb. So you see that the occupants had a large effect on ozone, as they did in that simulated office experiment I showed you, really bringing the ozone level down. What about the SOA? Well, unoccupied, the level of SOA reached about 5.5 micrograms per cubic meter. Now, this is not a terribly high level, but remember the air is being passed through building filters. So the air is being filtered, and it's a recirculating system, so there's multiple passes of the air through the building filters. So even with filtration, the SOA reached about 5.5 micrograms per cubic meter unoccupied. When the room was occupied, the level of SOA was lower. It only got up to between 2 and 3 micrograms per cubic meter. Now we actually had conflicting things going on. We were making some particles because of ozone reacting with the human occupant. But the human occupants were bringing the level of ozone down, and that reaction between ozone and limonene is a major source of SOA. It's much more important in terms of SOA production than the reaction between ozone and the human occupants themselves. So on net, we saw this reduction of SOA because the classroom was occupied. This slide describes recent experiments. The paper is on the web right now for indoor air. It doesn't actually have page numbers yet. These are experiments conducted by Lance Wallace and Wayne Ott, and I was fortunate enough to be able to participate on the sideline. And they did these experiments in their homes. Both are retired, and both have bought particle measuring instruments. They're very interested in particle formation and particle measurements indoors. And some of you have probably read papers by Lance Wallace and Wayne Ott. I know Professor Jiang knows them. At any rate, in these experiments, they took a small stainless steel pan. They actually looked at different pans, but here I'll talk just about the stainless steel pan. They took the pan and they repeatedly heated it on an electric burner till there were no ultrafine particles coming off of the pan. They then set the pan aside. Maybe the pan sat in the room for 3 days. Maybe it sat for a week. Maybe it sat for 2 weeks. They put it back on the electric burner. They heated it up for 5 minutes. They saw ultrafine particles again. So here's a pan that had been repeatedly heated until there were no UFPs coming off. They let it sit in the room air for a few days. They put it back on the burner, and they see UFPs. Where are these ultrafine particles coming from? Presumably, they're coming from organics that have soared onto the surface of the pan during those several days that it was exposed to room air. If we do a little math, looking at the flux of UFP from the pan and compare it to what we anticipate to be a reasonable flux for organic sorbing to the pan, things roughly work out. It's pleasing actually that things work out as well as they do. So this is a source of SOA that hasn't received much attention. Interesting, I heard from Bill Nasroff, a close friend, who'd been operating a particle counter in his home, that in the fall, when his heating system first went on, he saw a burst of UFP. And he thought that that was from the hot surfaces associated with the heating system, but he never had a chance to really investigate that in detail. The impact of air exchange on SOA formation indoors is a fairly complex topic. I said how important this reaction of ozone with limonene is. Imagine we have a limonene source in this room and the ozone is coming in from outdoors. What happens when you decrease the air exchange rate? Well, when you decrease the air exchange rate, you bring in less outdoor ozone, right? But you also do not remove the secondary organic aerosol from the room as fast as you do at the higher air exchange rate. Well, in the case of the ozone-limonene reaction, when you reduce the air exchange rate, the SOA goes up. Even though you've reduced the amount of ozone being transported from outdoors to indoors, even though the ozone concentration goes down because you've reduced the air exchange rate, the SOA goes up. The ventilation is that important in terms of removing the SOA from indoors. In the case of the ozone-limonene reaction. Now, in the case of the ozone-limonene reaction, the yield goes up at lower air exchange rates, which is consistent with what we understand regarding yields and the ozone-limonene reaction and how it depends on the concentration of particles in the air. The air exchange rate impacts ozone-limonene more than it impacts the ozone-alpha-pinene reaction. And we can understand why if we look at the structure of alpha-pinene and the structure of ozone. Alpha-pinene has just one double bond. So when ozone reacts with a molecule of alpha-pinene, that's it, it's done. But limonene has two double bonds. So let's say ozone reacts with this double bond in the ring. That opens the ring, and you get some of the low volatility product contributing to secondary organic aerosol. But you've still got another double bond. You've got this double bond. And ozone can react with that double bond on the molecule resulting from opening this ring, and you get still other products. So you have secondary chemistry that's important for SOA formation in the case of limonene that you don't have in the case of alpha-pinene, which is why you have this different impact of air exchange, because air exchange has a really big impact on secondary processes that require more time. Surface films are very important indoors, and yet we know very little about them and their nature. We know that they're a mix of organic and inorganic constituents, but if we were to look at this on an atomic level, are we talking about a homogeneous film, or do we have islands of inorganic species and islands of organic species? What's the phase state? Are we talking about an aqueous solution and something that's like a liquid organic? Or are we talking about something that's a bit glassy and a ligamer? We don't know. A lot of work has been done studying these questions for airborne aerosols, surface films, and it's the same kind of questions. And it's very important because this will likely influence the chemistry that occurs in these surface films. Indoor organics partition between the air and these surface films. We know that from measurements. We can predict the concentration of an indoor organic in a surface film from its gas phase concentration and a partition coefficient. And it turns out that we can estimate this partition coefficient surprisingly well simply using the octanol air partition coefficient. The fact that it works so well tells us that the surface film must in some way have properties that are similar to octanol. Let me show you just how well this simple process works. This is work conducted with Bill Nazaroff, and we took advantage of a database available from the US EPA. The US EPA had a large study in Ohio and North Carolina, in schools and in homes, where they measured a number of species simultaneously. They measured between 15 and 20 semi-volatile organic compounds, primarily pesticides, in the air, on surfaces. Skin wipes. At any rate, here we had this database where we had air concentrations and surface concentrations for 15 to 20 SVOCs. And we looked at how well we could predict the surface concentration using just the gas phase concentration and the octanol air partition coefficient. So the y-axis in these different plots, that's what we predict using this simple approach. And the x-axis, that's the actual value measured by the US EPA researchers. Notice that the units for the x-axis are nanograms per square meter, and the units for the y-axis are nanograms per cubic meter. So they're measuring a surface concentration, and we're predicting a concentration in the volume of the surface film. So the intercept in these plots is actually the thickness of the surface film. And it turns out that the thickness that we get with these intercepts is reasonable. It's on the order of 10 to 25 nanometers. Some measurements have been made of surface films by Miriam Diamond's group at the University of Toronto, and this is consistent with her measurement. There's many interesting questions regarding surface films. I mentioned this question of phase. I think another question is, what is the role of transition metals? First of all, what are the dominant transition metals present in surface films? What's their oxidation states? What are the ligands? If you know the oxidation state and the ligands, you know what the major complexes are. Do these transition metal complexes play a role in indoor photochemistry? If you've got iron alkyl hydroxide complexes, we know they photolyze to produce the hydroxyl radical. Is this happening indoors in surface films? In the dark, do we have pentene chemistry? The classic chemistry mediated by the iron-3, iron-2 couple to again produce hydroxyl radicals? We don't know. But I think in some cases this chemistry is probably important. We do know actually more about chemistry that occurs in HVAC systems. Think about what happens on a building filter. It captures particles, and those particles have organic compounds associated with them. So now you have these organics associated with the particles sitting on the filter, and they're accumulating, they're building up over time. And what's passing through that filter? Outdoor air. And on a day like today, the outdoor air is maybe 70, 80 ppb ozone. I mean, there's the potential for chemistry, and we've measured some of that chemistry in experiments at the Technical University of Denmark. But there's a lot more to learn regarding the chemistry that occurs on the surface of filters. Something else that's been observed on the surface of the filters is dehalogenation of brominated or chlorinated compounds. An example is a flame retardant, Deca BDE. So PBDEs, those are polybrominated diphenyl ethers, very common flame retardants. Deca BDE, Deca brominated diphenyl ether. So 10 bromine atoms on these two rings. Deca is considered to be a relatively safe compound. Penta was the first PBDE used in large amounts. It's not used anymore because it's considered to be toxic. People are concerned that some of the pentacongeners are endocrine disruptors. But Deca can lose bromines and become penta on the surface of a filter. This is not good. Finally, I think an interesting question is the potential formation of nitrate radicals from ozone reacting with NO2 in ventilation ducts. If you've got lots of ductwork, the transit time is long enough that we might be able to form reasonable amounts of nitrate radical. And of course, it's dark. You don't have to worry about photolyzing the nitrate radical. So, potentially interesting chemistry. We know the first two bullets happen. The third bullet is just hypothesis. Another example of surface chemistry, in this case something that's been measured and is somewhat scary, is what happens to cigarette smoke that's deposited on the surface of a room. People now talk about third-hand smoke. And when they talk about third-hand smoke, they're talking about this deposited smoke that has reacted with something like nitrous acid to make nitrosamines. And I think you appreciate that certain nitrosamines are potent carcinogens. It's not a good thing to be making nitrosamines. Two carcinogens have been identified in third-hand smoke. NNA and NNK, you can see their names at the bottom of the slide. In studies of human cells, in vitro studies, third-hand smoke has been demonstrated to increase oxidative stress and to be genotoxic. In studies with mice, the third-hand smoke has been demonstrated to increase lipid levels in the liver, not good, to increase levels of inflammatory cytokines in the lung, to reduce the lengthening the amount of time required for for healing of a wound, and it makes the mice more hyperactive. For whatever reason, I don't know. Transformation of carbonyls to imines is something that's known to occur outdoors. There's been some nice studies over the past 3 or 4 years on the transformation of carbonyls to an imine. It occurs in the presence of ammonia, and it's been demonstrated for the ozone-limonene reaction. Well, I think this chemistry has to occur indoors. The ozone-limonene reaction is so common indoors. We get these different carbonyls from the ozone-limonene reaction indoors. And we often have significant sources of ammonia indoors. Think of babies' diapers. Diapers, there's lots of ammonia coming off of diapers. Think of something like litter box for a cat. There's lots of ammonia coming out of that litter box. So the conditions are right. What's interesting, going back. The researchers who studied this outdoors have been demonstrating that when an aqueous droplet containing carbonyl and ammonia evaporates, the reaction accelerates tremendously, as much as a factor of 1,000. Well, indoors we have wet-dry cycles that occur on surfaces just because of day-night changes in temperature in a room. So you have the same potential to accelerate this reaction when an aqueous surface film evaporates. I'd like to conclude by saying a little bit about what I find to be exciting, the fact that state-of-the-art outdoor instruments are being used now indoors. So those results I presented regarding the hydroxyl radical indoors from the photolysis of Hono, I said that that was done using laser-induced fluorescence. Coralie Schumacher and her group from France are using LIF-phage in different indoor environments, trying to better understand hydroxyl radical concentrations under different conditions. And I think we're going to see some interesting papers coming out of this group. They were among the co-authors in that PNAS paper. Jason Ham and Ray Wells at NIOSH have constructed a cavity ring-down spectrometer with the help of Steve Brown, and they're starting to use that in indoor environments to try and measure nitrate radical. If they're successful, it'll be the first time that we have measurements of the nitrate radical indoors. Somewhat surprising when you think that we've talked about nitrate radicals indoors for 30 years, but we have no real-time measurements. Michael Waring and Peter DeCaro at Drexel are starting to use aerosol mass spectrometry to examine chemical constituents of indoor aerosols. And they're looking particularly at how aerosols change as they're transported from outdoors to indoors. John Abbott and his team at University of Toronto are using direct analysis in real time, DART, coupled to a mass spectrometer to examine chemistry on surfaces. So I'm excited about this, and I think we've got a lot that we'll be learning from these groups. Well, you've been patient. Thanks for listening as long as you have. I've taken a little longer than I intended. I get carried away. I like this topic. Chemistry is chemistry, but different conditions indoors from outdoors result in different processes dominating indoors compared to outdoors. I've just mentioned these state-of-the-art instruments, and I think we have a lot to learn from these instruments, and we also have a lot to learn by applying what we've learned outdoors in terms of chemical mechanisms to indoor situations. In terms of especially fruitful area for research, I think photochemistry, oxidation chemistry, hydrolysis chemistry, surface chemistry. These are really rich areas for future investigation. Indoor and outdoor chemistry are strongly coupled, and I think each discipline has the potential to inform the other, and actually I'd like to be one discipline rather than two different disciplines. Well, thank you for your attention, and I'll be happy to try and answer questions.
Any questions?